Check, check, check. All right. So welcome back. We are on lecture 18. We're going to talk about using linear elastic fracture mechanics in a design scenario. And this is still for static loading, but this is kind of a nice background for thinking about linear elastic fracture mechanics when we get to cyclic loading. We'll add it on to our knowledge of what we already know. So I'm going to go through just a few different charts and ways of using some of the equation that we came up with in the last lecture. And then we'll try to do an example problem toward the end of class. So we came up last time with an equation where we had a fracture toughness, and we were calling that K. And we equated that to some geometric factor, we'll call it C, times a local stress, times the square root of pi times the crack length A. And we said that we were going to use kind of the uniaxial tension mode 1 crack opening as our most extreme case, and so we'll stick with that today. And so because of that, we'll be calling this K1, right, for mode 1 crack opening, which was that Pac-Man situation where there are forces directly pulling the crack open. And then we'll have a geometry factor based on that. And then the same, our stress times square root of pi times the crack length. So how do we come up with these geometry factors that come into here? Right. Well, they really are based on how, as I said last time, kind of a definition of this fracture toughness is how far field stresses are concentrated at the crack tip. Did I say something wrong? Is there a question?
So then, is C the same thing as square root of pi, like from the last lecture?
No. So the question was, is C the same thing as the square root of pi from the last lecture? No. For some reason, the book is introducing multiple sort of like forms of equations that all have a constant C out front. And so, no, it is not.
Okay, thank you.
Sure. And so this geometry factor is helps us to translate how those faraway stresses affect the local crack tip stress. And so what we're going to do is we're going to start thinking about some dimensions here. So I'm going to draw up our example specimen under uniaxial tension. That's evenly distributed, so it makes a nice uniform axial stress. And then we'll start putting some dimensions on this. So there's a crack in the center here, and it's a through the thickness crack, so it goes all the way through into the page. And that crack length here, the way that they have defined this geometry is that it has a length 2a across. So actually a is half of our crack width. It doesn't really matter with the nomenclature, but the way that the charts in this text are designed, that's how they define a. So it's sort of symmetric around a center line with a on either side. So 2a is the crack length. And then the width of the entire plate, they're calling B, 2b, so on either side is b. And then the distance in the far field to where the crack tip is going to be h. So if we go all the way out to the ends of our specimen, wherever those are, we can call that dimension 2h. And we assume that h is approaching infinitely larger than a or b. So there's no local effects from those loads applied at the end. Okay. So when we start thinking about these factors, what we really care about is how big the crack is with respect to the rest of the specimen. So on the x-axis is going to be the ratio A over B. So that's the ratio of the length of the crack to the width of the plate. Okay. On the y-axis here, they give kind of a complicated term. And it's going to be this c that we care about, in this case c1, times the square root of 1 minus a over b. So rather than factor in the a over b on the x-axis, they've put it like this on the y-axis to, I guess, to make the plotting a little bit easier. The ratio a over b goes from 0, right, which is no crack, up to 1.0, which means that the crack has propagated through the entire length of this thing. And so for mode 1, oh, and it goes up to a maximum of 1 here. And it's going to go down to 0.6 here. And so there's a line that goes from just a little bit above 0.6 straight to 1, but that's for mode 3. So let me just put mode 1 on here. So it's a little bit above 0.8, like this. And there's a little bit of a dip, and then it goes up to about 1 like that. And so the way that we use this is if we have a crack and we know the length of the crack, the length of the width of the plate, then we come over and find that on the x-axis, right? So let's say that the length of this, just start putting some numbers and intuition here. Let's say that the crack is half the width of the plate. So it's this red line on the bottom of the plot. So we would follow it up, and then we would read off this other term. And then we can write down that C1 times the square root of 1 minus a over b was 0.5 is equal to whatever the value is that we read off. So somewhere right between 0.8 and 1, we'll call it 0.9. I did not do the math on this before class, so let me just plug that in real quick and see what it is. Okay, so I think if I've calculated this right, we get C1 is equal to 1.27. So that means we can, we would plug that into our C1 here, and if we know the nominal stress, then we can calculate what the fracture toughness is for this situation, and then we'll compare it with some critical fracture toughness that we're given for the material property. And then if this value that we calculate is greater than that value, we would expect that this plate would come apart very quickly. If that value is smaller, we would expect that this crack is stable and it's not expected to propagate. Yes?
Where does that graph come from? Is it experimental?
The question is, where does the graph come from? Yes, unfortunately it is sort of empirical. Yep.
And it's not material dependent?
It's not what?
Is it not material properties dependent? So for any material that works?
Correct. This is not material property dependent. Let me just think about that before I comment on it. So I believe anything that would be material dependent would be found when we're comparing with the critical fracture toughness for a given material. That these are only the geometric effects that we expect to be at sort of the continuum level. right? So we assume this is a homogeneous linear elastic solid. And so if we make those assumptions, then this is generally what comes out of it. And then we compare that with the critical fracture toughness for a particular material. Yep, it's a good question. All right, so that was for mode 1. There are also lines for mode 2 and mode 3, but I'm not going to go through those in detail because it's the same procedure. And so this is for a central crack that's kind of encapsulated that goes through the thickness of the material. Because these are empirically derived, there are yet further charts on if the crack is an edge crack. All right, so I can draw another schematic here. Okay, it's a little bit not symmetric here. But now we have a crack on either side of length A. And everything else is kind of the same. We have a uniaxial load here. We have a width of the plate 2b. Okay. So for this type of situation, the plot looks a little bit different. So before we kind of saw that it had like a local minimum and then it went up. So in this case, it does not have a local minimum and go back up anywhere between 0 and 1. And the y-axis is extended up above 1. So for mode 1, we kind of have 0.6, 1, 0.8. So we kind of go from here all the way down to here. And this is a generally decreasing curve, but it's not linear. So this was also for mode 1, where the definition of this is C1 times 1 minus the ratio, square root of that. Okay. So you can see now that if the crack is very small, then we have a different type of effect where we might even calculate a C that's very close to 1. Right? So you can start to build your intuition as to how the geometry of where the crack is affects this fracture toughness. Right? And there's actually a nice problem at the end of the chapter, which I think I'll put in a problem set that has you compare if the same size of crack is in the center of the plate versus the edge, which is the more intense situation and would cause failure first. So this is, that's for mode 1 for edge cracks. We can also talk about mode 2, mode 3 for edge cracks. And this would be if there are symmetric edge cracks. Okay. The curve looks different if we have a single-sided edge crack just on one side. And one of the most common situations that occurs is an edge crack on one side because of a bending loading, right? So I'll draw up this schematic here. So we'll have a plate with only one edge crack of length A. And instead of having a tensile force on this, we're just going to have a pure bending moment that's symmetric on both sides. Okay, and we're going to say the width of the plate is B here, just for definition's sake. So you can see now, if I draw sort of a center line down here, that our crack is on the edge, right? So it's going to experience an opening, mode 1 opening, if the beam is bending in that direction. And at the crack, it's going to experience kind of a tensile and a bending that will contribute to the crack opening. Okay. Give me 1 second. Okay. So we know that the stress at that point, right, that is a critical point. If we go back and think about all of our other types of failure modes, right? So the bending, the stress due to bending there, right, we can write it as something like this, 6m divided by t times b squared. And that's great. But if we go back and we think about our equation, that's like this, where this is now the bending stress and pi square root of pi times a. What do we use for this situation here in terms of both the bending and the tensile load that's there? Right? So you can see how this situation is inherently different from just the plate being put under tension. Okay. So what we're going to do is actually calculate both, okay, and then superpose them. So the K1 total is going to be equal to the K1 for the tensile mode plus the K1 for the bending mode. And so that's what we would then compare to the critical K1C for a material property. And we would have to look at 2 separate charts. First, we would have to look at the chart for the tensile loading. If we calculate what is the tensile stress there at the edge, and then calculate what that C would be. And then we also have to look at a chart for bending and calculate what that C would be because of this combined situation. Okay. The last thing I wanted to mention is another really common situation, which is a crack emanating from a hole in a plate, okay, and biaxial tension. Because this is like every riveted joint or bolt hole through a plate or something like that. So here's a situation in which we would have stresses pulling on this plate. So we can call this stress in this direction just sigma. And then we can call the stress in a perpendicular direction. Right, that can be like a function of sigma, right? It can be like some, some lambda times sigma, some constant, or you can have a different stress. It doesn't really matter what you use as the notation here. But if we define it as a lambda sigma, right, then our sigma 1 and sigma 2, right, our principal stresses will be all in terms of one stress and then a multiplication factor. Okay, and so then if there's a hole in this plate, right, like a bolt hole or something like that, it's going to have a radius r. And then let's say there's a crack coming out of the edge here, Okay, so maybe the tension on the plate, or there was some defect there or something like that, has created some crack coming out from that hole. So we can call that length A. And so we kind of have this distance from the center of the hole out to the edge here of R plus A, right? So we get a handle on some of this geometry. And so if we want to think about what is the mode and what's the stress on this, if we think about mode 1, then it's really only in the direction of this sigma here. So we can say that for mode 1, if there's a tensile stress, the K1 is equal to that C1 times the stress only in that direction times the square root of pi A. Right? So it really does simplify down quite a bit. And then it'll have a different type of a chart to look at. So instead of A over B as we had before, we will have A divided by R plus A on the x-axis. So it's kind of like, what is the extent of the crack with respect to the size of the hole that was there initially, right? Rather than with respect to the entire dimensions of the plate, because the plate could be very wide across the width. And then on the y-axis is some different factors that have some interplay between this stresses in both directions, okay? And so if we have, let me just look at this again. So there's a little bit of a different definition for C1 in this case because of the two stresses. So in the book it says that C1 is equal to 1 minus lambda times some F naught plus lambda times F1. So this is basically like a partitioning of this geometry factor based on how different the stresses are in the perpendicular direction of mode 1 opening and then the parallel direction of mode 1 opening. And so the plot that we use to look at this now is in terms of like F naught, F naught or F1 are on the same chart here. Okay, so like these kind of factors are here. And then you would look at whichever one you cared about. Like there's one line for F naught and then another one for F1. And they kind of like come together like this. So then you would read those off and then put that back in to the C1. Okay. So that's kind of what I wanted to talk about as far as just how to read these kinds of charts. And now let's do an example problem where we're going to be using this so you can get a better intuition of some of the numbers that are involved. Okay, so I'm just going to read this problem statement and sort of draw it out. So it says a 7075 T6 aluminum member, of rectangular cross section. Okay, so it's 0.38 inches thick by 4 inches wide, 20 inches long between pinned ends. Okay, so I'll draw like kind of 4, 20. It's a little bit longer than it is. But. So let's say 4 inches, 20 inches, and it has a rectangular cross section like this, where this is 4 inches. And I've clearly drawn this not to scale. This would be 0.38 inches. Okay. Between pinned ends, so, okay. It's subjected to a static tensile loading during operation. All right, so if we draw kind of this. All right, so pinned ends. Not sure that one might be on rollers. Okay, and then static tensile load. Okay, if inspection of this member has shown a 0.15 inch single edge through the thickness crack, what is the maximum allowable tensile load that may be supported if a safety factor of 1.5 is required? Okay, so through the thickness crack, right? So it extends through all the way through 0.38 inches, and it goes from, it's a single, what does it say? Single edge through the thickness crack. So it goes all the way through the thickness, and I'm just going to draw like a crack here so we can use that as our example, right? So the A of that crack is 0.15 inches, and it goes all the way through the thickness, right? So if we look at an end-on view, yeah, it goes all the way sort of back through there, all the way through the thickness off of one edge. Okay, so there are actually two ways that this thing could potentially fail, right? The load might be high enough such that you actually get yielding of the remaining cross-sectional area, right? So we've cut off some of the cross-sectional area, but the red here is still supporting all the load. So we need to check for just static yielding first, and then we will use the equations that we have to check to see if we would expect this crack to propagate and the whole thing to fail by brittle fracture. So we'll check both of those things. Okay. So it says, blah, blah, blah. What's the maximum allowable tensile load that may be supported by the member if a safety factor of 1.5 is required? Okay. So let's go back and think a little bit about our failure theories, right? And so we have a very simple situation where we just have a tensile load. So we don't really need to go through all the calculations of calculating the maximum shear stress or the von Mises stress and those kinds of things because we just have a uniaxial tension in one direction, okay? So our allowable load divided by the area is going to be our allowable stress, and we'll just say that we're comparing that stress to the yield point, okay? Okay. So let's do this. Let's say our load is P, capital P, and our allowable load is going to be equal to whatever the allowable stress is times the area. And our allowable stress is going to be the yield point divided by our safety factor of 1.5. So this is our failure criterion for just static yielding. And so if you want to think about this, sometimes in undergraduate classes, we refer to this yield stress as a yield stress in tension. So sometimes you'll use that when you're talking about threaded fasteners and things. You'll have a yield point in tension. So if you want to do that, you can assume that this is the yield point in tension. Okay. So then we can say our allowable load is a failure stress, in this case the yield stress, divided by the factor of safety times the nominal area. And so let's put some of those numbers in. If I said for this aluminum that our yield point was 75 kpsi, our factor of safety is 1.5, then, yeah, it's not inches, it's just 1.5. Then the nominal area is where we need to be a little bit more careful. So we know that the thickness of this thing is 0.38. So that's one dimension that we have. That's in inches. And then the other dimension is our 4 inches, but it's minus that 0.15, right? So this is what I mentioned in the last lecture about making sure you calculate the nominal area correctly. So 4 minus 0.15, these are all in inches. Right, so then we could calculate, we can do that arithmetic, and we come up with an allowable stress of 73.2 kilopounds or 1,000 pounds. So, okay. So that's a pretty high load. And so, okay, now we need to compare that with what the load would be if we were thinking about brittle fracture and what we've just looked at. Okay. So, okay. So I gave some equations in the last class and these charts that we talked about in this class, and they assume a plane strain approximation. So that means the plate is sufficiently thick in order to make those assumptions. And so we had a threshold, and I realized I spelled plane strain wrong in the last lecture after I was informed. So plane strain approximation, which was the thickness of the plate B has to be greater than or equal to some critical fracture toughness divided by the yield point squared. So let's calculate what that is here. Oh, I forgot it. There was a factor of 2.5 out front. Whoops. Okay. All right. And so it would be 2.5. And for that same material that had a yield stress of 75 kpsi, it has a fracture toughness of 26 kpsi. So we can square that, and we come out with 0.3 inches. Okay. Our thickness was 0.38 inches, so it is in fact thick enough to use this plane strain approximation. So that's kind of just a check. Okay, so our equation that we are going to apply, our failure criterion for brittle fracture, is going to be the, K1C, right, is ours will be greater than that. So for failure, we need to stay below it. So let's just write this as an inequality. Okay. Yeah, the example problem doesn't write it as an inequality, but they should. Okay, so for us to stay safe, we need to stay below that, less than or equal to our geometry factor times the stress for, we can write like brittle fracture or something like that, keep track of that, times square root pi a. And then what we really care about is the stress, and then we multiply times the area to get the critical load. Right? So I'm going to rearrange this equation and solve for the stress. So stress has to be less than or equal to K1C divided by, that C should be over here. Get that together. Times square root pi a. And then if we think about our charts, our A over B, A was our crack length of 0.15, and B is our plate width here, so it's 4. So we have actually quite a small ratio here, 0.0375. And then the chart for this one, if we read, I'm not going to go through it in detail, but you all can read a chart. So we read the chart and we do the math. We come up with our C1 here is 1.13. So our crack is quite small compared to the plate. So we only have kind of this multiplication factor of 1.13. So now our stress, we can start plugging the numbers. Our K1C was 26 kpsi. Our C1 is now 1.13. Square root pi times crack length 0.15 inches. Okay, and that would be kpsi square root inch. Sorry about the units there. Okay, so then for this, we come out with the stress has to be less than or equal to 33.52 kpsi. The square root inches cancel out because they're on top and bottom. And then our allowable load for brittle fracture is going to be this stress here divided by our factor of safety, if this is our kind of metric that we're using. Let me just get this right. Times the area, right? Stress times area is load. So we have 0.38 times 4 minus 0.15. Okay. So then our allowable load here, I'm just going to make sure, I'm just going to check this number real quick. Okay, so I get 32,000, about 690 pounds. Okay. So this value is quite a bit smaller than what we got if we just checked for yielding, right? It's like sort of 32 compared with the other one, 73,000. Okay, so it's less than half of what is allowable. So for this particular problem, right, this is a plate that you could kind of hold in your hand. So it's like kind of, 20 inches long, 4 inches tall, and then has a really tiny edge crack. So if we pull on this thing with 32,690 pounds, the crack will propagate and will fail due to brittle fracture, okay, due to that pre-existing flaw. So this was just a sort of an example of how to predict whether this plate is going to fail and in what mode, okay? So anything that has a defect in it now has two possible modes of failure rather than yielding or an extension of yielding would be like the blowout of a full component like a pressure chamber. And now it has, if it has a flaw, it also has the possibility of brittle fracture. We could go back and calculate what would be the load that would not just yield this plate, but would break the whole thing apart. And it would be higher than the yielding load, right, if this is a ductile metal. And so that doesn't come into play here. So yes, question.
So for the allowable load, the book doesn't subtract the crack length away from that.
You are right.
Is that something that we should be doing, subtracting the crack length away?
So in my opinion, yes. I have seen it both ways in textbooks. Okay. This flaw is very small, so I knew it wouldn't change the number very much. But I'm actually working off the book example, which you saw. So this is at the end of chapter 3. They give some examples. And so I did not calculate, I did subtract it off because I figured it would be more conservative than if I left it on there. So if you do not subtract off the thickness, or the width of the crack, the 0.15, the length of the crack, then you get a value of almost 34,000 pounds instead of 32,500 pounds. But in this case, yeah, I just wanted to be a little bit more conservative. Yep. Okay, good. So this is the ending time for the first lecture today, so I'm going to call it there, and then we will pick back up I did want to tell you I have another obligation this afternoon, so we're not going to have a second lecture today. We will have a makeup lecture tomorrow, and then all of our lectures next week. But we're going to end here for today, so I'm glad that we got this lecture recorded.